Okay. So good morning, everybody. I'm going to give just a few minutes for folks to arrive. Today, Haley and Tahara are going to teach us section 3.1 from the textbook. And I think I have pretty much everything set up and ready to go. I want to queue up the videos here, and that way I can stream them through Zoom to you guys so we all see everything at the same time. We don't end up with people pausing. We're getting out of sync. So give me just one moment here. I will turn on my screen share. This is, of course, still MAC2311, section OH1. And today is the 25th. So we'll be looking at the power rule and derivatives of exponential functions. Let me see where we're at here. All right, I do want to wait until Tahara is here. Give me just one moment. I'll turn off my screen share. I can double check my email, make sure everything is going okay with her. And I will also queue up the videos. Okay. All right. All right. So Haley, I'm going to go ahead and follow the link that you gave me, that YouTube link, and we'll make sure everything is here in a playlist. This looks good. All right. And then the other thing that we're going to need here, let me get Tahara's videos. I know she was working on potentially re-recording these with a slightly better focus on the board. But it's okay because if she hasn't gotten those set up yet, that is okay because the videos she sent me last week are still just fine. We just have to listen carefully as we go through them to make sure we don't close these. To make sure we're not missing what's being written. So if you have any hard time seeing anything, please don't hesitate to ask me to pause and we can make sure everybody's able to get everything down. Okay, this should be good. Should be good. While that's loading, I will pop up the other one. Okay. Yeah, all right, we are in like Flint here. This is looking good. I may try to download this video while Haley's is playing. That way we don't have to worry about possible buffering issues coming in from that end. I trust that YouTube will buffer things reasonably well. So while this plays, desktop OH1. Okay. Start downloading this one also. Save file. just leave it here. This is video. Interesting. Okay, how are we doing? Everybody here? Tahara, you made it. Okay, I'm so glad. All right, don't worry. I got your email saying that you couldn't get back into the school to re-record. Don't panic about that. The videos you sent me are okay. We will work with them. It's not going to be a problem. And I am excited for all of us to see the beautiful hard work you guys have put in. So I'm going to go ahead and turn on my screen share here. I think I've got everything queued up. We're good to go. So we're going to start with Haley's videos. She talks about derivatives of constant functions and then the derivatives of power functions. And then after we get through each of Haley's videos, we can stop and take a few questions. Once we finish with Haley's videos, we're going to move on to Tahara's videos, and she's going to teach us how to get derivatives as combinations of functions. So if you know the derivative of f and the derivative of g, how do you get the derivative of f plus g, that sort of stuff. And then she's going to talk about the derivatives of exponential functions, which turn out to be very, very nice. So please, guys, pay careful attention, take very careful notes, just as you would if it was a regular lecture. And then after each of these little videos, we're going to stop and take a few questions. Can everybody see my screen okay?
Yep.
All right. I'm going to go ahead and start playing here. I'll play for just a few seconds, verify that we can hear everything.
Today we will be starting with section 3.1 out of the textbook. So section 3.1 focuses on how to differentiate or take the derivative of constant functions, power functions, polynomials, and exponential functions. In the next few videos, I will be going over how to differentiate constant functions and power functions, and then Tahara will be focusing on polynomials and exponential functions in her section. So this video is about the constant function.
Okay, I'm going to pause here for a second. Can everybody hear and see everything fine? Are there any problems with the stream? I'm going to take your silence as complicit acceptance. Everything is good?
Oh, good.
Okay, excellent. All right, then we're going to let this roll, and I will stop for questions at the end of Haley's first video here.
And the constant function is written as f of x is equal to c, where c is a constant. It's preferable to write it as a positive integer because they're just easier to work with, but really c is just a number. The graph of f of x is equal to c is written as y equals c, which is drawn as a horizontal line with a slope of 0. And all horizontal lines have a slope of 0, so the constant function will always be written and drawn like this. So I'll give you a minute to copy this graph down. It's pretty simple to draw, but it's important to recognize what the constant function is right off the bat based off of its graph. Okay. So to understand how to take the derivative of the constant function, we can use the definition of the derivative, which is f prime of x is equal to the limit of h approaches 0 of f of x plus h minus f of x over h. And we can substitute in our constant function, which is f of x is equal to c, such that the limit as h approaches 0 is of c minus c over h. And because c and c are equal, we will end up with just 0 in our numerator over h, and that is equal to 0. So just like how the slope of our constant function is 0, the derivative of f of x is equal to c is also 0. We can understand that f prime of x is equal to 0 because f of x equals c and has a slope of 0. So the tangent lines of a horizontal line are probably the same. They're written or drawn about the same. So when you think about it, we're finding the graph of the tangent line of a horizontal line, and it's going to have the same value of 0. So some examples of how to use how to take the derivative of the constant function are here. So find the derivative of f of x is equal to 3. Well, 3 is just some number. It is just a constant number. So if f of x is equal to 3, then its derivative will be 0. f of x is equal to 476, even a super large number. We don't like to look at really big numbers in calc. We prefer easy to work with numbers, just in any math class, really. But even the derivative of such a large number is still 0 because it is just a number, it is just a constant value. The graph of y is equal to 72. Again, it doesn't matter how big our number is, as long as it is just a number, its derivative will be equal to 0. And we just have one more example of f of x is equal to the square root of 9. The square root of 9 is 3 plus or minus 3, which is just a number again. So any graph of any constant function will have a slope of 0, and therefore its derivative will always equal 0. So if there are any questions, feel free to ask them after this video ends. You're welcome to go back and watch this video again. If you need me to slow down, you can just pause the video at any point to write down anything you might have missed. In our next videos, we will be going over the power rule and power functions and how to take the derivative of such. Thank you.
Alrighty. So I'm going to pause here and come out of the video for a second. Are there any questions for Haley on that first video or the concepts therein? The idea that the derivative of a constant function is always 0. So again, the basic idea, and Haley nailed everything beautifully here. No matter where you choose to look, no matter what a is, if you come in here on the graph of a constant function, the tangent line is always horizontal. It's always the same as the line that you're looking at. So the slope of that tangent line is always going to be 0. The proof there was perfect. F of x plus h is c. F of x is c. Because no matter what the input is, x, x plus h, 5, 7, 12, the output is always the constant value c. So the limit that defines our derivative is the limit as h goes to 0 in f of x plus h minus f of x all over h. That numerator is just c minus c. So that numerator is always 0. So you end up with lim h to 0, 0 over h. And we can't plug in h equals 0 here because there's still an h downstairs. But just algebraically, if you have 0 divided by anything, if the top really is the constant 0, 0 divided by anything is always 0. So you can simplify this fraction to 0 before taking the limit. And then the limit as h approaches 0 of 0 itself is always 0. Each of those examples is really good. These are all constant functions, right? The output from each one of these guys is just a constant. It doesn't care what the input is. And so that all of their derivatives will be 0. This middle, the second to last guy here, the notation is nice. I like that you use the Leibniz notation for one of these. We'll talk a little bit more about Leibniz notation towards the end of the day here when I wrap up. But this dy dx is the same thing as f primed. It's just written in that alternate notation. So I'm going to come back to the video. Are there, again, any questions for Haley or myself so far? All right, then I'm going to come back here and let this play. And this one, we're going to look at power functions more generally.
Hello, and we are back for part 3. So we are still in MAC2311. We are going over section 3.1. We have talked about the constant functions. We are still talking about power functions. In the last video, we looked at how to find the power rule. We found the power rule taking the derivative of 3 different functions to different powers.
I think this is the wrong one.
We out of order?
2 and
I'm
3.
sorry. Here, let's see.
That might have been my bad with uploading the wrong.
So let me leave this open, but I'll poke around in here. So you want part 2, right? I think that one is labeled as part 2.
So you want part 1. So it's power rule part 1,
Okay,
but it's part 2 of my entire
I got
lecture.
you.
I'm not sure how I
No,
only
you're
have
good. I
those
found it here.
3.
We got it. We're golden.
Okay.
Hello and welcome back to MAC2311. We are still going over section 3.1. In our previous video, we looked at the constant function and how to take the derivative of such. And in this video, we will be starting to look at power functions and how to find the derivative of those. So get through constant function and we reach the power function. So the power function is written as f of x is equal to x to the power of p, where p is a positive integer exponent. Now, the textbook uses the letter n to signify exponents, but we use p just because it is more different than the letter h, which is often used in the definition of derivative. And when we're handwriting it, n's and h's tend to look the same. So p
Good choice.
is nice to use to demark a positive integer exponent or any integer exponent. So using the definition of the derivative, we can find the derivative of a power function. Again, the definition of the derivative is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So using this, we are going to go through a few examples of how to differentiate a power function because we don't have the power rule yet. We haven't determined if the power rule exists, what it is, what it means. So we're going to go through these examples where p equals 1, 2, and 3. So for the function f of x is equal to x to the power of p, let's start with p is equal to 1. So using the definition of the derivative, we have the limit as h approaches 0 of x plus h to the power of 1 minus x to the power of 1 over h, which is the same as the limit as h approaches 0 of x plus h minus x over h. And this first x and this last x are going to cancel because this is a positive x, this is a subtraction of a positive x or the addition of a negative x, whichever one makes you feel better. So our first and last terms are going to go on vacation and we don't have to look at them again. So we end up with the limit as h approaches 0 of h over h, which is the same as 1, quantity of 1. Now, while we're going through these examples, we want to be thinking, what is the value of the exponent in our answer when compared to our original function? That will help us notice the patterns that we are looking for. So when p equals 2, we have the limit as h approaches 0 of quantity x plus h squared minus x squared over h. And when we FOIL this quantity squared term, we have the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. And once again, we see that our first and our last digits are going to cancel. We see that our first and last terms are canceling. We don't have to deal with them again. So the next step is to pull an h out of that 2xh and that h squared term so that we can then cancel the h's from the top and the bottom. So we reach the limit as h approaches 0 of h multiplied by 2x plus h over h. These cancel, leaving us with the limit as h approaches 0 of 2x plus h, which is the same as 2x when we plug in 0 or h. So once again, think about what is this a power? What is the power of this term? 2x to the what? Think about it. Our last example is when p is equal to 3, we have the limit as h approaches 0 of quantity x plus h cubed minus x cubed over h, leaving us with the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed over h.
I am going to pause here just for a second to make sure everybody has time to write this down. This calculation is a little bit painful, and I know that that when I have to cube this out, it's going to take me just a second. So I just want to hold here for 1 second to let everybody catch up in their notes. Everybody doing okay so far? Any questions on the calculation? Has anybody noticed any patterns yet?
Yeah, it's always like it's up for factoring and expanding the binomials.
Yeah, exactly. So after we cancel the leading term and the trailing term here, which is always this guy, we're left with something we can factor out. And then after we factor out that h, which is always common to the kind of middle terms, the answer here seems to have an interesting form. The 3x squared is this term, this coming from the second to first term after we factor the h. And then what was the exact pattern you noticed there after factoring?
It would end up like with a polynomial of degree 2, and then like the final answer would just be like that term to that degree.
Perfect. Yep, that's exactly correct, right? The degree goes down by 1, and then the old degree becomes the new coefficient. Is everybody comfy on where the x cubed plus 3x squared h plus 3x h squared plus h cubed, the first 4 terms in the second line here, are coming from? That's coming from foiling out this x plus h 3 times, right? X plus h times x plus h times x plus h. It's a bit of a big messy algebra thing to do. And there's a fast way to do it using what's called the binomial theorem. And I think Haley's going to talk to us a little bit more about that when we get moving here. But I just want to make sure everybody had time to write down. Is everybody good? All right, I'm going to resume play in 5, 4, 3, 2.
Again, as always, our first and our last terms are canceling. They seem to always do that. Let's hope that that is true. So we can pull an h out of the 3x squared h, the 3x h squared, and the h cubed terms, leaving us with the limit as h approaches 0 of h multiplied by 3x squared plus 3x h plus h squared. The h's in the top and the bottom will cancel, leaving us with the limit as h approaches 0 of 3x squared plus 3x h plus h squared is when we plug in 0 for h, leaving us with 3x squared. So I'll give you a minute to write these down. I'll go back to the last slide. I'll give you a minute to write these down if you haven't already, and we'll move on to the next slide. And think about the patterns that we have found using these 3 examples. Okay, and here's the last example. If you haven't written it down yet, I highly recommend that you write these 3 examples down because they will help you recognize the pattern that we're looking for when differentiating the power functions. So the thing that I've been hinting towards is that the exponential value of our solution is 1 less than where we started. So we started with f of x is equal to x to the power of 3 in example 3. And we ended with f prime of x is equal to 3 times x to the power of 2. So 2 is 1 less than 3. The same happened in all of our previous equations. Let's look back at those. So in our first example, we had f of x is equal to x to the power of 1. And x to the power of 1 is just x, as we see in our second step here. And when we end up with just 1, what is 1 in relation to x to the power of 1?
X to the 0.
1 is the coefficient of x to the power of 1. So when we end up with just...
That's a good observation here, that you can think of this as 1 times x to the 0. So if you want to add that in there, this is a nice thing to consider adding to your notes. Oh, sorry.
That means that we have 1 times x to the power of 0, which would just be 1 times 1. We can pretend that we have a little x here to the power of 0, and that helps us see the difference in our exponential values. That's 1, it would be 0 over here in our imaginary x. It's 1 less than where we started. And same in our second example, we have 2x as our solution, that is x to the power of 1, when we started with the power of 2. 2 minus 1 is 1. All right, so pattern recognition. The pattern that we notice is that our exponential value of our solution is always 1 less than where we started. And from this, we have discovered the power rule, which states that f prime of x is equal to p times x to the power of p minus 1. This first p is equivalent to our original exponential value. So if we have f of x is equal to x squared, we have the 2 in front, 2 minus 1, leaving us with the 2x, just like example 2. So yes, please write down this power rule. The power rule is super important in this unit. It will be very helpful in the rest of this class. If you've taken calc before, this isn't anything new to you, but it is a friendly face to see. It's nice to see the power rule coming back to us. All right, moving on. So our next video is going to focus on how to prove the power rule. We will be learning about the binomial theorem, which is a tool that we use to take the derivative or to derive the derivative of the power rule. So I will see you in the next video. If you have any questions on this video, please let me know and ask me and ask the professor, and hopefully we can answer them as best as we can. I will see you in the next video. Thank you.
Very nice. All right, I am gonna, let's see here. We'll jump to this, I'll pause. So the thing that we've conjectured here is certainly true, and I would suggest adding it to your notes as a theorem. If f of x is equal to x to the p, then f primed of x is equal to p times x to the p minus 1. And this is the power rule. And Haley, you described that all beautifully. Everything there was lovely. Every time I thought, oh, I need to insert a comment here, you had it right there. This is very, very nice so far. Does anybody have any questions for Haley on those first 2 videos, or any of the notation, any of the results or calculations? So in the start of the next video, Haley's going to be working with what's called the binomial theorem. And that is an important tool. And she's going to give an abbreviated version of it, but I just want to show you the full thing here. It says you can take something like x plus h to the p and expand it, right? Just like you can FOIL out x plus h squared, x plus h cubed. There is a general formula for these. It's just quite scary looking. It's the sum from k equals 0 to p of p choose k times x to the, we'll write it like p minus k times h to the k. And if you write this out, this is p choose 0 times x to the p plus p choose 1 times x to the p minus 1 times h plus p choose 2 times x, let's see, times, I'm doing this right, yeah, times x to the p minus 2 h squared. And you keep going down here. The second to last term would be p choose p minus 1 x to the 2, I'm sorry, x to the 1 times h to the p minus 1. And the last term here would be p choose p times h to the p. And the really important thing to observe in all of these is that this term has no h's. This term has one h, has h to the 1. This and all of the other terms, all of these have h to the 2 or higher powers of h. The little things you see in here, p choose k, this, these are called binomial coefficients. And they're defined in terms of the factorial function, p factorial over k factorial times p minus k factorial. And in practice, the way we can usually write these is as p times p minus 1 times p minus 2 and so on, down to p minus k plus 1. P minus k, or p minus k minus 1 if I wanted in parentheses like that, all divided by k times k minus 1 times k minus 2, all the way down to 3 times 2 times 1. The first few of these that we're going to need, she will show you in the video, but p choose 0 is always 1. P choose 1 is p. P choose 2 is p times p minus 1 over 2. And the patterns kind of continue like this. All right, so this is our binomial theorem. And we're going to use a somewhat simplified version of this in the proof where she replaces these actual pieces by what they are, so the calculations don't look so scary. But if you've seen the binomial theorem before in pre-calculus, it's the same binomial theorem. You may have seen these defined in different ways. There's lots of ways to define binomial coefficients. The most helpful thing for raw calculation is usually what's called Pascal's triangle, but I'll save that for another time. So I'm going to let Haley go ahead and take over here again with her videos. And this is a very nice proof. So please, let's pay attention and make sure we take really good notes.
Hello, and we are back for part 3. So we are still in MAC2311. We are going over section 3.1. We have talked about the constant functions. We are still talking about power functions. In the last video, we looked at how to find the power rule. We found the power rule taking the derivative of 3 different functions to different powers, where p was equal to 1, 2, and 3. So this video is going to focus on proving the power rule, proving how we take the derivative of power functions, and how we can follow the same steps every single time, no matter what our power equation, a power function, looks like. So we're going to skip through the slides that we've already looked at, and we find ourselves looking at the binomial theorem. So I'll pull myself up a little bit. All right, so the power function uses the binomial theorem in its proof. And the binomial theorem is quite daunting. I'm not a fan of it, but it is necessary to prove our power rule. So the binomial theorem states that for every quantity x plus h to the power of p, we can expand this function to x to the power of p plus px to the power of p minus 1 multiplied by h plus p multiplied by quantity p minus 1 over 2 multiplied by x to the p minus 2 multiplied by h squared plus a whole bunch of other terms that have h to the power of some number, some quantity, and our last term is h to the power of p. So these all have an h in it. All of this section has the variable h in it. And it's okay to write it as plus plus h to the power of p, because we will eventually be plugging in h into our equations, and when we plug in h as a limit, usually is 0. So if you have any further questions about the binomial theorem, please ask the professor. I've tried my best to understand it, but I'm still a student just like all of y'all, and I will admit that I do not fully understand the impact and the importance of the binomial theorem quite yet. And that's okay, because this is my first calc class in college, and I feel like we're all in the same boat, being a little confused by the binomial theorem. So we'll hopefully be able to ask the professor a little bit more about this. So we reach our proof, and this can be a little hard to read. I was having quite a bit of computer trouble making this presentation, but hopefully you can read it, and I will read it out loud as we go through the steps of our proof. So if f of x is equal to x to the power of p, then f prime is equal to the limit as h approaches 0 of quantity x plus h to the power of p minus x to the p over h. So this is the definition of the derivative. And to expand this x plus h to the p minus x to the p, or just this, we are just expanding x plus h to the p, because in this last slide, that is all this is. This is the first term in our numerator of the definition of the derivative. So let's get into it. So when we expand this, we find that the limit as h approaches 0 of x to the power of p plus p times x to the power of p minus 1 over multiplied by h plus p times p minus 1 over 2 times x to the p minus 2 times h to the power of 2 plus a whole bunch of other terms that have the variable h in it. We do not have to write it. You can if you want, but we don't really need to. We don't worry about all of that. We're focused on the patterns that we find and proving how to differentiate a power function such as this. Minus x to the power of p over h. So this last term is just this minus x to the power of p. That's all this is. From here to here is our binomial theorem, expanding our first term of our numerator. And we can simplify this by canceling our first and our last term, that x to the p and the subtraction of x to the p, leaving us with the limit as h approaches 0 of p times x to the power of p minus 1 times h plus p times p minus 1 over 2 times x to the p minus 2 times h squared, plus a whole bunch of other terms with h in it, plus h to the power of p. And just like in all of our examples in the previous video, we are pulling out the h. We're pulling out one h out of all of our terms in our numerator so that we can cancel it with our denominator. So we have the limit as h approaches 0 of h multiplied by the quantity of px to the power of p minus 1 plus p times p minus 1 over 2 times x to the p minus 2 times h plus a whole bunch of other variables or terms with variable h in it plus h to the p. And when we cancel that h in the numerator and the denominator, we are left with just the binomial theorem here.
I am going to make a short pause here, and I don't mean to interrupt the cadence. This is going very nicely. In not this line, but the line below here, once we've factored out this h, the h from the first term will be gone. The h from the second term, that h squared, will become an h. And then this very last guy, all the powers here of h are getting reduced by 1. So this would actually be an h to the p minus 1. It's just a tiny little typo. But if you're taking notes here, I'd like to make sure we get it down correctly. The move from this line to this line is factoring out an h. And that means the power of h in every one of these terms is going to go down by 1. So this will be a p minus 1 here.
Variable. So we have the limit as h approaches 0 of px to the power of p minus 1 plus p times p minus 1 over 2 times x to the p minus 2 times h plus a whole bunch of other terms with h in it plus h to the power of p. And when we substitute in that 0 for h, all of these terms, this term here, this big nasty one, becomes 0 multiplied by 0, it becomes 0. All of this plus blah, 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 blah terms are multiplied by 0 because h is being substituted in with 0. And this
Beautiful.
is also substituted as 0, leaving us with the limit as h approaches p, or h approaches 0, excuse me, of p times x to the power of p minus 1. And this is still our power rule. It's p times x to the power of p minus 1. So I will give you a minute to write all that down. I know I talked pretty fast, so let's just look at this. If you're having trouble reading this, I can write it on a piece of paper and take a picture of it and send it to you or post it somewhere after this video. I can't get it any clearer on my screen
Oh,
either.
you're good. You're good. Yeah, this is beautiful.
So yeah, if you have any questions about how we proved the power rule, feel free to ask after the video, and I will do my best to explain it. Once again, we are highly reliant on the binomial theorem, and if you don't fully understand the importance of the binomial theorem or where we got that from, please ask. I don't fully know where the binomial theorem came from either, but we're all in this together. We're all learning together how to differentiate power functions. So, all right. And if you need more time, you can always go back and watch these videos later. So there are some special cases for power functions. These special cases are when p is no longer a positive integer exponent. Yikes. So sometimes p can be negative. We can have negative exponents, and we can also have fractional exponents. Fractional exponents usually look like a square root. When something like x is raised to the power of 1/2, that is the square root of x. We learned that in like our algebra classes, our pre-calc class. But if you're still struggling with fractional exponents or even negative exponents, I highly suggest using like Khan Academy or some other sources to practice that, because they can be tricky to learn, but very easy to identify once you have learned them. So we're going to look at a couple examples of where p is negative and where p is a fraction. So when our power, our exponent p is negative, we can still use the power rule. So find the derivative of f of x equals x to the p when p is negative. So f of x is equal to x to the power of -1. When we use the power rule, which is f prime of x is equal to px times, or to the power of p minus 1, then we can substitute that in. So f prime of x is equal to -1, which is our p, times x to the power of -1, still our p, minus 1, which is the same as -1 times x to the power of -2, so negative x to the power of 2. I don't know a prettier way to write that. I'm sure there is one, but this is fine.
Just a quick comment. If we wanted to, we could write that as -1/x². So everybody should be writing these examples down, right? These are our first few kind of challenging examples for the power rule. And what we've shown here is that the derivative of the function x to the -1, which is 1/x, is f primed equals -x to the -2, or -1/x².
If it's not fine, someone please let me know. But
no, this is fine.
in my previous calc class, we just didn't care. Once we got our answer, we're like, oh, that's fine. But please let me know if that's not okay.
Yeah, that's okay. But we can rewrite it as -1/x² if we wanted.
Exponents, find the derivative of f of x is equal to x to the power of p when p is a fraction. So I think I went over this a little bit in the last slide, but when f of x is equal to x to the power of 1/2, and the power rule states that f prime of x is equal to p times x to the power of p minus 1, then we just substitute that in, and we have f prime of x is equal to 1/2 times x to the power of 1/2 minus 1. Our coefficient remains 1/2 multiplied by x, and when you subtract 1 from 1/2, you end up with -1/2. So that's 1/2 times x to the power of -1/2. Generally, you can make this look like 1/2 times the square root of x, or the negative square root of x, I believe is what it would look like. But it is up to you how far you simplify your solutions.
I'm going to stop here for a quick comment, just because I do want to talk about the algebra. I know you guys are all really good at your algebra. This is an honors class. But the two examples there are really good examples. So we had f of x is x to the negative 1. This is the same as 1 over x. So if we were told to differentiate 1 over x, our first step would be to write it as x to the negative 1. And then by the power rule, f primed, p here is negative 1, so we would have p times x to the p minus 1, which exactly as Haley did it, this would be negative 1 times x to the negative 2. And if we wanted to, this is the same as negative 1 times 1 over x squared, or negative 1 over x squared. And there will be moments where simplifying things like this are important. The second example that she did there is really good also. But let's pretend like it was given to us in this form. We want to find the derivative of this guy, or any other rooting function like this, cube root, square root, fifth root. That is x to the 1/2. And so again, by the power rule, f primed would be that power, which is 1/2 times x to that power minus 1, so 1/2 minus 1. And Haley's calculation here is perfect. This is 1/2 times x to the negative 1/2 power, which is 1/2 times 1 over x to the positive 1/2 power, which is 1/2 times 1 over the square root of x. So we could write that as a single fraction if we wanted, as 1 over 2 square roots of x. And these sort of simplification steps are not crucial to getting the answer correct if all you're interested in is the derivative itself. But later we will want to do things with the derivatives. So these simplification steps, while they're not crucial right now, they will be useful down the line. So it's worth taking the time, I would say, to add them to your notes here. Everything Haley did is correct, is perfect, but I do want to add these additional steps just to make sure we're comfy. And then the other note I would like to make here is that while the problem may be given like this, it might say find the derivative of the function f of x equals x to the negative 1. It could also be given like this. And if we have something like this, we need to first rewrite it like this in order to apply our power rule. And the same thing is true here. If we're asked to differentiate f of x equals the square root of x, we need to first rewrite that as a power function before we can apply the power rule. So there's a neat kind of take-home message here, and that's if you're trying to differentiate a function, your first thought should be, can I write this as a power function? All right, so 1 over x, can I write that as a power function? Yeah, that's x to the negative 1. Okay, I know how to do that. Square root of x, can I write that as a power function? Yeah, that's x to the 1/2. Okay, I know how to do that. And then the calculations flow exactly as they were in the video. Any questions on those notes? Any questions on the simplification steps at the end here? Moving this term downstairs to make the power positive, and then rewriting as a root. Alrighty then, I'm gonna come back to Haley's video. We'll let this finish up.
Some of the homeworks might require us to simplify it more, but generally computers are good at understanding what we mean, even if it's not fully simplified. So I believe that is all I have on the power function. I will give you some time to write all of this down and to maybe write some more notes to yourself regarding special cases. But these cases prove that the power rule is always usable. We can always use the power rule when we have a power function. When we have any function that is f of x is equal to x to the power of some number, we can use the power rule, thanks to our proof, thanks to these special cases, thanks to the binomial theorem. So again, so if you have any questions, please feel free to ask after the video. In the next videos, Tahara will be discussing how to take the derivative of polynomials and exponential functions. So we can't wait to learn about those. If you need any help, I am not an expert. I definitely suggest asking the professor and using external resources. Maybe look at the textbook as well, and even check out Khan Academy. There are some helpful hints and tips in there, especially when dealing with different types of exponents. It's a simple algebraic skill that a lot of us looked over in our previous math classes that I find very important. So yeah, I hope you learned something from this. I hope you found this helpful and that I did an okay job here.
Very nice.
And I will see you guys later.
All righty. So we don't need quantum axioms. We can hold off on those. But yeah, this is very nice. So are there any questions for Haley or myself on the power rule, its statement, its proof, or its uses?
Yeah, I have a question for Haley, but it's not necessarily on the topic. So, Haley, yeah, you did like an excellent job. I was just wondering, so you did this like through like a PowerPoint, and then you screen recorded it and then sent it to YouTube, or how exactly did you get?
Right. So originally I had written everything out on a whiteboard, taken pictures of it, and I was going to do a voiceover. And then my camera decided to delete all of my photos. So then I rewrote everything into a Google Doc because they have a option to write equations. That's why the proof is kind of iffy looking because it was written in Google Docs. And then I took screenshots of that Google Doc and then put it into a PowerPoint and wrote in the PowerPoint so that it could be more streamlined. And then I opened a personal Zoom meeting and screen shared my PowerPoint and then spoke over it so you could see a picture of me and the PowerPoint as we went through it.
That is a nice way to do this, right? So you can host your own Zoom meeting and then record that Zoom meeting to your computer. And it's a nice way to generate videos with screen shares or other overlays. Yeah, I agree. The production value there is very nice. You did a wonderful job. Any
Got
other?
it. Thank you very much.
Are there any other questions about the power rule or questions for Haley? All right, then. I will go ahead and queue up Tahara's video next. I think her first video is going to be showing us how to get derivatives of combinations of functions. So if you know a couple of derivatives, how do you get the derivative of the sum of those functions or the difference of those functions? I have them set up to stream from OneDrive, but I also downloaded them here. Hopefully they've downloaded, that way we don't have to worry about OneDrive being silly if it is, because sometimes it is. So let's see here. Is this going to play nicely? Can't play. The file isn't playable because the type is unsupported. I was worried about this. This is nonsense. So there should be an MP4, right? Properties. I'll try this one. No, no dice there. All right, so we are going to have to stream this through OneDrive. That's okay. This will work okay. But the resolution may suffer a little bit. So if you guys have any trouble reading or seeing anything here, I think the resolution as we stream from OneDrive sometimes falls off, especially since I am simultaneously streaming it up to you. Just go ahead and holler if you have any trouble seeing anything, or if we need to pause for a second.
Hello everyone, this is Saharanya Mesempara, and I'm going to do my presentation about exponential functions and derivatives.
Let's make sure our screen share is on.
And show some.
So I'll pause here for a minute. Can you guys see that, or is the screen share? No, it's not on, is it? Yeah, all right. Here we go. And then we want to get rid of the picture in picture. And we should be good to go.
Notations of the derivative.
Is everybody able to see and hear? I'll pause for just a second. Can we all see and hear okay?
Yep.
Okay, beautiful. All right, I will let Tahara take it from here.
So, okay, let me adjust this. So first, let let y equals f of x equals to then the derivative can be written as so as I was saying, there are many notations of the derivatives. Some might put it like y prime or f prime of x or d over dx, right? And some even put it like b and a. Or ways to write derivatives. And if you are even taking or have taken physics, they also write it this way. So the most common ways to write derivatives in math are usually the first two ones. That being said, I'm going to give some simple or basic rules about derivatives. So if f of x equals b, when I say if f of x equals b, I mean if f of x is a constant, then f prime of x is 0. And if f of x is a constant, the derivative is automatically 0.
I do want to pause just for a second to make a comment on the notation here, because the notation is something that people can get a little confused on. Tahara is right. There are so many different ways to write derivatives, and all of those different things she showed there are used fairly commonly. But there's a slight difference, and it's kind of a grammar thing that I'd like to inject here just for a second. So the f prime notation is what we've seen mostly so far. And if you want to write this in the Leibniz notation, we would normally write this as df dx or dy dx. And these are the same as saying like capital D sub x of f of x. And that would in some settings be the same as f dot from physics. So these are all the different notations. The note I wanted to make here is the difference between ddx and dy dx. And when I say this is a grammar thing, this is what I mean. This is what's called a differential operator. And you can think of it as a verb or an action word. It says differentiate whatever is next to me. And this guy is the actual derivative. This is the derivative of y taken with respect to the variable x. So if we're talking about actual equivalencies, f prime of x would be df dx or dy dx if you're thinking of f of x as being y. The ddx itself here is the differential operator, and it's a nice way to write things. Think of this as being the same as just the prime. So f prime is df dx or dy dx, and the prime symbol on its own, just the prime symbol, is ddx. And then d dx is the same as this capital D sub x. So this would be like d dx of f of x. So there are a lot of different notations here, but this contrast between the d dx where the numerator is just a d versus the dy dx or df dx where the numerator has something else besides just a d upstairs, this guy here is a noun. So this guy is the derivative. This guy says take the derivative, and it's a slight difference in grammar, really, which is a weird thing to see in mathematics. But Tahara's doing a wonderful job here showing us all these notations, and I'm going to let her continue without any more interruption.
And derivative of x prime of x equals 1. Okay. If of x goes x to the n, then x prime of x equals n times x to the n minus 1. So let's say if f of x equals 1, then f prime of x is 0 directly. No calculations needed. Okay. And if L of x equals x, that's already written. F of x is equals 1. And let's say 3x. Then f prime of x is equal to, you can even apply this rule. 1, 3 times x to the 0, which is 1, and f of x equals 3. Well, those are basically the main rules, or simple, basic, but main rules to note with derivatives. And, and if f is a differential function, d of x, d over d of x of c f of x equals to c times d derivative of f of x. So let's say if you had derivative of 3x, for example. Let me change that. Let's do 3, no, 4 x to the fifth exponent. So that equals to 4 the derivative of x to the fifth, which is equal to 4 times the derivative of x to the fifth is 5x to the fourth, right? So n times x to the n minus 1, which is equal to 4 times 5 is 20, 20 x to the 4. That's the answer. Yeah.
So sort of this first rule that's going to help us get new derivatives from old derivatives is the fact that constant multiples pop out. You see here on this line, this is really the sweet sauce here. If you're differentiating a constant times your function, that constant can pop out. It's the same as that constant times the derivative of your function. And in the example down here, 4 is the constant. So we want to differentiate d dx, the function 4 times x to the 5. So that 4 is a constant multiple. He's just like the c in the line above. He will pop outside the differential operator d dx. And then we apply the differential operator d dx to the function x to the 5, and we get 5x to the 4. So the 4 pops out, comes along for the ride, and then as a consequence of that power rule that we just learned in the last video, the derivative d dx of x to the 5 is 5x to the 4. So we're kind of doing two things here. We're using this new notation, the d dx notation, the differential operator, and we're using the power rule from the previous video together with this constant multiple rule. So this rule right here, that d dx of c times f of x is equal to c times d dx of f of x. That's our first big rule for cooking up new derivatives from old derivatives.
So let's say if you had derivative f of x plus g of x, that's the same as derivative on f of x plus the derivative of g of x. So basically, or you can even write f times x plus g times x. Let's do an example of that. So if we can the derivative for x to x to the 8 or your x to the 8 4 x to the 4 plus 7 x to the third times 6 x plus 5. So we're gonna have the derivative of x to the 8 plus the derivative of 12 x to the 8 plus the derivative of, actually this is negative because we have minus 4x, a negative here, 4x to the 4 plus the derivative of 10x cubed minus the derivative of 6x plus the derivative of 5. Right?
Perfect. So if we want to differentiate a sum or difference of functions, we can split that up over addition or over subtraction. That's what this sum rule here is telling us. And then down here in this example, we have 1, 2, 3, 4, 5, 6 different functions all added up. and I want to differentiate the whole mess. So this sum rule, together with our constant multiple rule, tells us we can split this up and differentiate each piece on its own. In other words, this differential operator, ddx, plays nice with addition and subtraction. So we can split up over all of this addition and subtraction and differentiate each piece.
So the derivative of 3x to the 8 is going to be 3 times 8x to the 7 plus 12 times the derivative of x to the 50 is 5x to the 4 minus 4 times 4x to the third plus 10 times 3x squared minus 6 plus 0. So 24x to the 7 plus 12 times 5 16x to the 4 minus 4 times 4 is 16x cubed plus 30x squared minus 6. That's derivative. So
All right. So really quick, I'm just writing these down over here in case anybody's having a hard time seeing. In that last example, we wanted to differentiate this big combination of functions. Using the two rules that we have, that constant multiples pop out and that you can split up over addition and subtraction, we get here. So in each of these, I've split up all of the addition. So we've got the derivative of the first piece plus, and then I popped the constants out from each of the others. So I pop out the 12, and then you've got the derivative of x to the 5, that's this piece. Split up over the subtraction, pop out the constant 4, and then we're left with the derivative of x to the 4, and the same for the remaining pieces. This is exactly what Tahara was doing on the board there. And now I apply the power rule to each of these little power functions. That's the idea, is that this polynomial here is built up out of little power functions. So the derivative of x to the 8 is 8x to the 7 plus, then we have 12 times the derivative of x to the 5, which is 5x to the 4, minus 4 times the derivative of x to the 4, which is 4x cubed, minus 6 times the derivative of x, which is 1, plus the derivative of 5, which is 0. And so we'd end up here with 8x to the 7 plus 60x to the 4 minus 16x cubed minus 6. And in general, this is how derivatives work. You can split up over addition and subtraction, and after you do that, you can pop out constant multiples. The 12 is only attached to the x to the 5, so in the answer, the 12 will only be attached to the derivative of x to the 5. The 4 is only attached to x to the 4, so in the answer, the 4 will only be attached to the derivative of x to the 4, the 4x cubed. But each one of these pieces can be differentiated on their own using the power rule from Haley's video. So Tahara is taking what we learned in Haley's video and combining it with these rules, that constant multiples pop out and that derivatives can be split up over addition and subtraction. Oh, I left off my prime. So I'm going to go ahead and start Tahara's second video, which is on derivatives of exponential functions. And we might go a little bit over time. I will ask you guys to please be patient with us. This is our first day of student teaching. These are really brave people who decided to go first here. So let's show them that respect and hang in, even though we're going a little bit over time. Let's see. Oh, no, we want to just play this if we can. Come on, come on. I'm going to turn off my share here just for a second to get this to work. All right. Here we go.
Hello everyone, this is me Tahara again, back with the second part of the video. I actually figured that I forgot to mention something. Or if f of x equals x to the n, f prime of x equals n times x to the n minus 1. I said that, but I forgot to put the multiplication one, which is if f of x equals c times x to the n. So f prime of x is gonna be c times n times x to the n minus 1.
And we can take
So
that
I
as a
think this is
consequence.
really
So this is really,
straightforward.
yeah,
And just multiply the constant by your actual
this is good. So we used that implicitly last
so
time.
the second video is going on the actual lesson, which is derivative of an exponential function. Okay. If I want to give the definition for definition of E. It is the number such that limit when h approaches 0, e to the h minus 1 over h equals to 1. That's the definition of E.
I know this is a slightly odd definition. It might not be the definition that you've seen in your pre-calculus classes, but it is a valid way to define the number
So
e. And it's what our textbook does.
f of x equals to E then f prime of x is gonna be equal to E of x. So, example where there is no change in the derivative and the starting function. So if you have f of x equals e to the exponent x, the derivative is still gonna be the same thing, e to the exponent x. Very easy.
So e to the x is your friend. He's the easiest thing in the world to differentiate.
If you have f of x equals the c times e to the x, your derivative is gonna be the same thing, c to the x. So I think that
So the bottom line there would be a consequence of that constant multiple rule.
there is the power rule, for example.
And it's important we don't confuse this with the power rule. So I really like what Tahara does
Exponential
here.
rule. The So this is something we can. For here we have y equals x to the n. In order to find the derivative for that, you're gonna do y prime equals n times x n minus 1. While here, your function is gonna be equal to x. You're gonna think we can do the same thing. Like y prime equals x times e x minus 1. And this is not correct because here the x is the exponent is n while x is down. And here, and so the y prime for this one is still gonna be the same thing.
So I want to come over here and make a few quick notes. The definition of the number e in our textbook is the unique real number such that the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. Here the number e is the number that you think it is. It's Euler's number. It's that 2.71828 blah 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 irrational number. And this limit is one way of defining that number. To prove the theorem, to prove that e to the x is its own derivative, we make use of this. So f primed of x here would be the limit as h goes to 0, f of, Einstein, f of x plus h minus f of x all over h. And if you plug in e to the x, then you get lim h to 0, e to the x plus h minus e to the x all over h. And now we need to do some algebra. This would be lim h to 0. E to the x plus h is e to the x times e to the h. And then you still have your minus e to the x, and everything is still over h. And now we can factor out an e to the x. And what's left is e to the h minus 1 over h. And this piece, by definition, is 1. So if I'm honest, this is kind of a weird thing that your textbook does, because everybody uses a different definition of the number e back in pre-calculus. We don't normally see this definition anywhere until you get to this section of Stewart. And then in this section of Stewart, he defines the number e to be the unique number such that e to the h minus 1 over h goes to 1 as h goes to 0. That definition is specifically designed to make this work, but it is a valid definition. So I wanted to show you why this definition is important before Tahara goes on to examples. It's because if f of x is e to the x, then the derivative has to be defined through this difference quotient. Here we're using an algebra rule that says like a to the b plus c is a to the b times a to the c. And then we can factor the common factor of e to the x out. This is e to the x times h minus e to the x times 1. So when you pull the e to the x out, what's left is e to the h minus 1. And this piece, by definition, goes to 1. So I'm going to move back over to Tahara's video and let her finish up. But I just wanted to show you guys why this definition is relevant here, because we need it to get this derivative to come out how it should. It's kind of backwards logic, but it is a valid definition, and I want to say that it is consistent with the definition you've seen in pre-calculus. I know we're a little bit over time, just a few minutes left. Please hang in there.
We have the tangent line. Let me give an example in order to find the tangent line. Okay, fine. Find equation of the tangent line. Of f of x equals to x plus 2x at the point two. Um, so first, in order to find the tangent line, we have to find the derivative of the function first. So here is our function. We have f of x equals x cubed plus 2x. So f prime of x is going to be, so this is x to the n, which is n times x, n minus 1. So we apply that rule, which is 3x, n minus 1, 3 minus 1, which is 2, and then plus 2. And we have if f of x equals c times x, the constant times the x, your derivative is the constant itself. We can even apply the same rule. It's like you're gonna do the exponent for this one is 1. So the 1 is gonna come out, multiply the x to the 0, right? Because minus 1 minus 1 is 0. So everything to the power 0 is 1. So 1 times 1 is 1. And then times 2, which is still gonna be 2. So you just take the constant. So here is our derivative. And then we're gonna find f prime of 2. So usually when we do find f of 2, f of 3, f of 0, you just plug the number in the function, right? So it's basically the same thing here. We have f prime of 2, but the only difference is it says f prime of 2, not f of 2. So you plug the number in the derivative, not the actual function. So which is 3 times 2 to the squared plus 2 equals 3 times 4 plus 2. F prime of 2 equals 3 times 4, 12, 12 plus 2, which is 14. And then we're gonna use, I know most of you know that equation, you have seen it in college algebra. Y minus y1 equals n x minus x1, right? Sorry. So basically, this is your n, like your slope. And the y1 and x1 are from this point, y1, x1, y1, right? So y minus y1, which is 12, equals n to slope 14, x minus x1, which is 2. So y minus 12 equals 14x, right? You expand that, 14x minus 28, y equals 14x minus 28 and you add 12 on both sides. So what's 12? Y equals 14x minus 28 and positive 12, that's gonna be negative 16.
Good. Yeah,
So
perfect.
that's the equation of tangent line.
All
So
right.
this is it for this video. I hope this was a help and have a great day.
Nicely done, guys. Okay, so we will go ahead and end class here for the day. Thank you guys so much for sticking around. I know we went over a few minutes. Next time, I'm going to show you some things, how to connect the definition of the number e you may have seen before with the definition of the number e used in our textbook, and we'll look at a few more examples of these types of things. Also this week, Thomas is going to be teaching for us the product and quotient rules. So I'm excited for you guys to continue. Let's express some gratitude. Normally, if we were in a class, I'd say we should all give a round of applause for our very, very brave people, Tahara and Haley, getting up here and doing the student teaching before anybody else has done it. I know that's a super high pressure and super scary thing to do. You guys both did really well. I'm very happy with the results here. Next time, I will show you a little bit of connection between the exponential function as defined in our book compared to the exponential function as defined in other books. And then Thomas is going to be teaching us the product and quotient rules. So yeah, really good job, guys. Don't feel bad about that video, Tahara. It's hard. You can see behind me here, I have a whiteboard. The first few semesters I tried to teach online, I tried doing that same exact thing. And eventually I gave up because I couldn't get stuff I was happy with. But I think everybody is able to see what we needed to see there, and everybody was able to get what we needed to get out of those lectures. So really good job, guys. Thank you for all the hard work you put into that. If anybody does have any questions, I have an office hour today from 1 to 2. And then next time, Thomas is going to show us the product and quotient rules. So take care, everybody. Have a great day. And if you do have any questions, don't hesitate to email or come by my office hour. I hope everybody has a lovely rest of your afternoon, and I will see you all on Wednesday. And then Thomas, if you could, I don't remember if we said today or tomorrow, but make sure that you come by an office hour so we can talk a little bit more before your actual presentation. All right, take care, guys. I hope you all have a good rest of your day.